Welcome back. So far, with regards to hypothesis testing, we have now covered how to do a hypothesis test to test a mean and a proportion. The next three sections, we are going to look at three special methods of doing hypothesis tests for really doing comparisons between two populations. In this section, we will cover hypothesis tests for the difference between two means, independent samples. So we've got a mean from two separate independent populations, and we do a hypothesis test to make a comparison about them. In the next section, we'll look at doing something similar for proportions. And then in the final section, we will look at, we will revisit the difference between two means, but we'll do it for samples that are not independent. So let's go ahead and dive in here. So we will again use the p-value method, but this time we will look at how to use the p-value method to perform a hypothesis test for the difference between two means. What we'll see is that the very basic structure of this test again remains relatively unchanged. In other words, our steps for conducting the test will still involve establishing our hypotheses, computing a test statistic, finding a p-value. But we'll tweak the formulas for doing these specifically for the context of difference between two means. So let's look at an example where this approach would be useful. So here's our example. Scores on the National Assessment of Educational Progress Mathematics test range from 0 to 500. In a recent year, the sample mean score for students using a computer was 309, with a sample standard deviation of 29. For students not using a computer, the sample mean was 303, with a sample standard deviation of 32. Assume there were 60 students in the computer sample and 40 students in the sample that didn't use a computer, so we can see that the sample mean scores differ by 6 points. Now we are really interested in the difference between the population means. Is it plausible that the difference between the population means could be 0? How strong is the evidence that the population mean scores are different? So what we have here is data from two separate populations, right? A sample of students who took this test and used a computer, and a sample of students who took the same test but did not use a computer, right? So the purpose of the hypothesis test is to explore whether allowing computer use on the test makes a significant difference in the outcome of the scores, right? So that's what the test will explore. So we have here an example of a situation in which the data consists of two independent samples. They are independent if the observations in one sample do not influence the observations in the other, right? They're completely separate from each other and they don't influence each other in any way. Now, when we establish the hypotheses, this time the hypotheses will be established as a way of comparing the population means from the two populations, right? Previously, recall, when we were just doing a hypothesis test about a single mean, the null hypothesis was a statement that mu equaled some number. This time, the null hypothesis will be the assumption that the two means are equal to each other. Now, in the context of our specific problem, remember that the null hypothesis is always the assumption that there is no change or no difference. And in our problem, that would be the assumption that allowing the use of computers does not make any difference in the outcome of the scores. And the way we would represent that concisely in the null hypothesis is by assuming that the mean score of those who use the computers is the same as the mean score of those who don't, or mu1 equals mu2. Okay? And then for these types of tests, the alternate hypothesis again can be either left-tailed, right-tailed, or two-tailed, but it's always set up as a comparison between the population means. right, as opposed to a single population mean being compared to a number, which is how we did it when we were just doing a test for a single mean. Notation, this is largely the same as what we've covered before, with the exception of we are dealing with two populations, so we have to have symbols representing the corresponding values from each population. And we do that by just putting subscripts of 1 and 2 on the symbols, right? So mu sub 1 and mu sub 2 are the population means. X bar sub 1 and X bar sub 2 are the sample means. S sub 1 and S sub 2 are the sample standard deviations. N sub 1 and N sub 2 are the sample sizes. So the test statistic. So because the standard deviations given are sample standard deviations, then the test statistic will be a t-value. Now recall that the basic format of the of any equation, whether it's z or t for the test statistic, it's always going to be the random variable minus the mean divided by the standard deviation. This time, the random variable that we want to explore is the difference between the two sample means, x1 bar minus x2 bar. This is a random variable that follows a distribution, and the mean of that distribution is the difference between the population means. It's basically an application of the central limit theorem, right? Remember, with the central limit theorem, we said that if we treat the sample mean as a random variable, it will have the mean of that distribution will be equal to the population mean, right? So a similar thing here. If the random variable is the difference between the sample means, then the mean of the distribution will be the difference between the population means. Now, if it turns out, and it can be proven mathematically, I won't walk through that, but the standard error, or the standard deviation of the random variable x1 bar minus x2 bar, is given by this formula right here. Square root of s1 squared over n1 plus s2 squared over n2. So then it would follow that the formula for the test statistic would look like this. x1 bar minus x2 bar is my random variable. Mu1 minus mu2 is my mean. And down here is my standard deviation, right? So random variable minus the mean divided by the standard deviation. And because the standard deviations are sample standard deviations, then it's a t-value. And the number of degrees of freedom is based off of the smaller of the two sample sizes, right? Remember that previously we said degrees of freedom is 1 less than the sample size. This time, though, we have 2 samples, so we would choose the smaller of the 2 samples and base our degrees of freedom off of that. Assumptions that have to be met here. We have simple random samples from 2 populations. The samples need to be independent from one another. And then each sample size needs to be either large, greater than 30, or come from a population that is approximately normal. So here is the steps we would follow for conducting the test. And notice again that these are the same steps, right? We're just tweaking them now. Specifically tweaking the formula for the test statistic is probably the biggest change here. But we still start by stating the null and alternate hypotheses. Choose a significance level alpha. Compute the test statistic using this formula. Find the p-value. And again, the p-value, if it's left-tailed, the p-value will be the area to the left of t. If it's right-tailed, the p-value is the area to the right of t. And if it's two-tailed, the p-value is the sum of the area to the left of negative t and to the right of positive t. And again, because this involves the student's t-distribution, if we're using the chart, the best we'll be able to do is kind of narrow the p-value down to within a range. If we want the exact p-value, we'll have to use technology such as the TI-84. Step 5, interpret the p-value, right? If making a decision, reject the null hypothesis. If the p-value is less than or equal to the significance level alpha. If the p-value is greater than alpha, then do not reject the null hypothesis, and then state a conclusion. So let's go back to our example, right? The National Assessment of Educational Progress tested a sample of students who had a computer in their mathematics classes, and another sample of students who had not used a computer. The sample mean score for students using a computer was 309, with a sample standard deviation of 29. For students not using a computer, the sample mean was 303, with a sample standard deviation of 32. Assume there were 60 students in the computer sample and 40 students in the sample that hadn't used a computer. Can you conclude that the population mean scores differ? Use the 0.05 level of significance. Notice that the word there is differ, so because it says differ, that suggests that we'll set this up as a two-tailed test. It is good to check our assumptions. We do have two independent random samples from separate populations. Both samples sizes are larger than 30, right? Yeah, 60 students in the computer sample, 40 students in the sample that hadn't used a computer. So those are both greater than 30. So our assumptions are satisfied. So then we'll establish our hypotheses. The null hypothesis is the assumption that the scores are equal to each other, right? There's no difference. And then because it says the word differ, the alternate hypothesis will be the assumption that the means are not equal to each other, right? And then kind of we summarize our the information that's given, right? X1 bar, the sample mean for those who use a computer is 309, S1 is 29, N1 is 60. X2 bar, the sample mean for those who don't use a computer is 303, S2 is 32, N2 is 40, right? And we plug the numbers into the formula for T. Now it's worth mentioning that mu1 and mu2 are part of the formula here for T, and we don't know what those values are. However, remember that when we are at this point in the process, we are assuming that the null hypothesis is true. The null hypothesis says that mu1 and mu2 are equal to each other. And if we assume they're equal to each other, then they will subtract to equal 0. So in the formula, we can just replace mu1 minus mu2 with 0. And we can plug in the rest of the numbers, right? 309 minus 303, put in your S values and N values down here. And if you work that out, you get 0.953. This is a two-tailed test, so the p-value is the sum of the areas to the right of 0.953 and to the left of negative 0.953. Okay. Really the best option for finding the p-value is using technology because it's the only way to get an exact value. If we do that, we get a p-value of 0.343. If you use the table to estimate the p-value, and this would be a good exercise for you to try at home just to get comfortable with the table, right? We would find our degrees of freedom would be based off of the smaller of the two samples, right? So we would choose sample size of 40, and that means the degrees of freedom would be 39, right? So we find the row in the table corresponding to 39 degrees of freedom. And then in that row, we find the two numbers that bracket 0.953. And then for both of those numbers, you'd go to the top of the table and find the corresponding area and right tail values. And then we would take both of those values and double them because it's a two-tailed test. And I believe if you do that, the table will tell you that the p-value falls between 0.2 and 0.5, which is consistent with the exact p-value of 0.943. Either way, this p-value is greater, significantly greater than our value of alpha. So we will not reject the null hypothesis at the 0.05 level, and we will say there is not enough evidence to conclude that the mean scores differ between those students who use a computer and those who do not. The mean scores might be the same, and we'll leave our answer as that. So that covers the basics of how to do a hypothesis test for the difference between two means using independent samples. We'll just kind of briefly touch on how to use technology. This shows a readout from Minitab. We don't really cover Minitab in this class, but that is another tool that can be used for hypothesis testing. For your calculator, if you were to use that, you would go to the tests menu on your calculator, right? Press the stat button, highlight the word tests, and the function that you would want to choose is the one labeled 2-SAMP-T-test. So scroll down until you see that. And again, we have two options for input, data or stats. Data would be what you would choose if you're just given the raw data. And then you would have to enter your data into your list editor before you access this. In the example that we just worked out, the stats would be the option you would choose because the sample means and the sample standard deviations are all given. And then you just type that information in, right? So you type in the value for x1 bar, s1, n1, and then x2 bar, s2, n2. Choose the option for a two-tailed test. For pooled, you would want to choose no. And then you would calculate, and the most important readout that it shows you here is the p-value of 0.343, which you can then compare to your value of alpha to conclude your test. Okay, so that wraps up this section. We've looked at how to perform a hypothesis test for the difference between two means using the p-value method.